I'm presenting our paper on neural morphology dataset and models for multiple languages, from the large to the endangered. So basically, like the whole idea here is to train neural models that can work side by side with rule-based FSTs. So if you look at the background of the whole thing is that we have Giella, the Giella infrastructure that does a lot of work for many endangered languages, and there are some other languages as well that are not endangered, like Finnish and German and Norwegian, that are supported in the infrastructure, but many of the languages are endangered, and the things they have is that they have FSTs, so finite state transducers that are rule-based morphological analyzers, generators, lemmatizers, like all in one. The good thing is that they kind of have somewhat consistent tagging across different languages. So, so basically, if you have some code for one language and then you try your code in another language in the Gela infrastructure, the tagging is mostly shared. The differences are usually just the language specific things, mostly like what kind of cases you have, what kind of inflectional forms, if you have dual, if you have just a plural or singular, or what kind of morphologies you have. And the thing is that these FSTs are used as building blocks for higher level things like constraint grammars, CGs, to do disambiguation, to do syntactic parsing. They are used for spell checking and such. So the good thing is that these rule-based systems are like very robust. If you have any problems, you can just go ahead and you can fix the rules, especially if you have the endangered languages. It's sometimes the only way to go about it. You don't have any data, you just write your rules and that's it. But then you kind of also have the other side of the rules. As we can see here, I'm trying out the Finnish morphological transducer, which is, by the way, it's very good. It's very extensive. Most of the time, if you throw a word at it, it knows what to do with it. And here is an example of one of my favorite words, suorituskyvyttömyysvakuutus. And it knows how to analyze it correctly. Like such a long word, most of the people wouldn't even know what it means. It's a type of insurance a construction company has to take just in case they cannot build the building they are about to build. So this is a word that like not so many people know, but the FST can still handle it, mostly because it's a compound word. But if you look at a word that is relatively more frequent in language, like Pikachu, it just doesn't know what to do with it. It doesn't have the word Pikachu in its vocabulary, and it doesn't give you any analysis at all. And that's a bit problematic because if we think about it, maybe most of the people know what the Pikachu is, and most of the people don't know what the suorituskyvyttömyysvakuutus is. So like really our end game here is not to come up with the latest state of the art, high F score, diba daba daba models, but we just want to be very practical here, and I want to enhance my Uralic NLP Python library. The Uralic NLP is a Python library for using these Giella FSTs and CGs in a very easy way so that anyone can use them. We are compiling them every night, so nobody has to figure out how to compile an FST from scratch. So I don't want to replace the neural models because the rule-based models, because obviously the rules are very important. You can fix them, and for endangered languages, you kind of want to have the models so that they describe the language as well and not just that they play a guessing game. But at the same time, I want to have some sort of a neural fallback model that if the rule-based model doesn't give me anything, then at least the neural model can give me something out. And there are like some practicalities that I have to take into account, like these models cannot be like overly complex. They have to be super easy to distribute, super easy to run, and there has to be some sort of a seamless integration with what we have already, which means that the tag sets should be the same as what we have in the Gela system. We cannot use, for example, Unimorph because the tag set is completely different and the complexity of the morphology is completely different what they have in Unimorph. So we are doing this in multiple languages. We mainly took all the languages that were supported in Giela that had an okayish FST, and they had a reasonably sized dictionary available in their dictionary platform. And as you can see, some of these languages are bigger ones, like we have German, we have Russian, Finnish, Norwegian Bokmål, Latvian, and then we have a bunch of smaller languages, Kven, Komisiri, and Moksha, Manziers, and so on and so forth. So a whole bunch of languages that kind of share the same tag set, so we should be able to do things. Now, the first question is that where do we get the data from then for all these languages? Well, none of these languages are probably going to have ready-made data sets with these Gela tags, at least not very extensive ones. But the transducers themselves, they have data. So just as we can toss a word to the transducer, it gives us the analysis. Why can't we give a lemma? It's part of speech, and then let the transducer tell us all the possible forms it knows. And we did this is actually required a little bit of like hacking and then like putting two transducers together with some regular expressions. But in the end, we implemented this in Uralic NLP. So you have this get all forms. If anyone wants to try out, you give it a word, you give it its part of speech, and you give it a language, and you get all the inflectional forms out. Now we are limiting this. We are not getting everything out. Here is an example. First, I ran this for Gold Sami and I didn't want to get compounds out, but I got everything else out. This is the word for piannai, which is a dog. So if we look at the long, lengthy word there, that's what the FST would output, this extremely long monstrosity. And if we are looking at the morphological tags, this kind of highlights the problem we are getting with this kind of FST approach, is that you will definitely have a lot of data, but I don't think that any Gold Sami native speaker could tell me what that word even means. Because as you can see, it's derived. There is the first thing it does is derives a diminutive out of it. Then it turns the noun into an adjective, adds a bunch of derivations. Then it's a verb all of a sudden with all these derivations. And then it kind of goes back and forth, going noun to adjective, then back to noun, then to verb, and then some diminutives here and there. And then it even introduces some orthographic errors in the way. So it was clear that we couldn't get everything out from the FSTs, or we would end up with a whole bunch of forms per word. And we cannot really afford that. And especially, it doesn't really make any sense to train a neural model to handle this kind of word that nobody would ever even know how to say, or would even write down. So for practical reasons, we are not taking compounds and derivations into account, although I would really like them to be there at some point in the future, and clitics. And then we definitely don't want to have any errors there, and we don't want to have any dialectal forms at this point of time. So in terms of data, here are the dictionaries we have. So the dictionaries have like different sizes depending on the language. We take all the words up to 2,100 words per part of speech for all the languages. We do the training and testing and validation splits on lemma level, which means that in the test set, we are not going to have any lemmas that the model saw during the training, because as we remember, our end game was that we want something that works with Uralic NLP. We want to have the kind of neural models that work with the words that the FSCs cannot handle. So we don't really care about whether these models can just fill in some gaps in the paradigm. We just want to know how well these models work for words that they have never seen before. And then we can see the degree of complexity also about there, like how many unique inflectional forms we are getting per part of speech category. And then you can see that for Finnish, there is a lot, and there is definitely a lot for verbs, like a whole lot of bias the model is going to learn from that. For training, we're doing a very simple thing. We're just taking OpenNMT PY and using the default settings otherwise, but we are using a bidirectional recurrent neural network instead of the regular recurrent neural network one. And this is the data we're going to feed to the model. So on character level, we give the word kauniinpansakko and then predict the output lemma kaunis on character level. For analysis, again, character level kauniinpansakko, output, this is not character level, but this is morphological tag level. And then for generation, character level word, morphological tag level to morphological tags, and then the output would be the kauniimpansakko, which is the inflected form of the word. And if you look at the results we got a whole lot of different things here, right? So for some languages, we get very, very good results. We get very good models, definitely seem to work. Then for other languages, it seems that the models don't work that well. And if we look at the kind of problematic tags, as we can see here in the table, the missing prediction shows the tags that the model didn't predict, but they were in the gold standard. Like these are the top ones. And the wrong prediction shows the tags that the model was predicting, but those were not the correct tags for the word. So first problem we can see immediately here is that for some languages, not all, but for some, the morphological analyzers, they also have these IVTV tags. And these are intransitive and transitive verb tags. And this is kind of problematic because then these analyzers they don't reflect the morphology that much. They reflect more of the morphosyntax. So they don't tell us what the current form of the word is. They tell us how this word can be used. And that is something that you cannot deduce. Like our neural model couldn't possibly even deduce that kind of information. So then like this kind of question is also that should we have the FSTs done in such a way that they only capture morphology and not morphosyntax? And if they are done in such a way, then we can actually train neural model with the same tag set, and it should work way better. And for some languages, you don't even have these intransitive, transitive tags. So as I said, we wanted this to be very practical. So now I have integrated all our models to my Neuralink NLP, and this is how you can call them. You just say neural fallback equals true, and then you get to use the neural model. And that's how it works, is that it first tries to use the FST. If the FST doesn't work, it uses the neural model. And here we can see some examples above for Finnish, where everything goes right. You want to generate a form for koirailla, which would mean that like act in a dog-like fashion, works well. Hörpähdin, which would be like get sipped. Maybe a cup of coffee could tell somebody that I got sipped yesterday. So hörpähdin works well. Nirhautan, I get killed, lemmatizes correctly. But then we get to what I wanted it to get right, which is Pikachu. And if we look at the analysis first, it tells me that it's a verb. And it's an active, indicative, present, and connegative. And this is actually plausible. If the lemma was Pikachua, then this is how you would inflect it in Finnish. You would say en Pikachu, I don't Pikachu. So the analysis is plausible, which kind of highlights the other problem, that can we then have these models even doing part of speech tagging correctly, because sometimes you cannot really deduce the part of speech tag. Sometimes you can, sometimes you can't. However, the lemma is wrong here, which kind of like then highlights the other problem, that now how we train these is that we train these with dictionary words for Finnish. We train these with the Finnish morphological analyzer, but then Pikachu is a foreign word, and it has the CH combination that no Finnish word would have. And probably C is even a character that was never in the training data, because Finnish words usually don't have the character C. So then Pikachu, instead of being lemmatized to Pikachua, which would be the hypothetical infinitive, it is lemmatized completely off Pikatua, which kind of makes us like think that, okay, maybe in the future we have to really rethink this for foreign words. So if you're interested, and especially if you think that you can do this better for the languages that we get very low scores, then by all means, go to our GitHub, see how to use the models, see how to get all the forms. You can also just go and download the models to yourself from our models repository, or the actual training, validation, and test data we used for all these languages. We have put it on Zenodo, free to use. Just go and go there. And if you get better results, it's great. And I hope we can integrate them with Uralic NLP. For some of the languages, we already get very decent stuff out. For others, I really want to improve the results. And I myself, I'm going to look into Finnish next, especially based on how I've seen the models operate with the Uralic NLP. So thank you very much for your attention.